Okay. So, chapter 1 is chemical measurements. Right. This is in many ways review. Like the last one was setting things up. There was fairly little review in it. A little bit, but fairly low. But this one is mostly going to be review for most of you because you've done it before because you needed to do it to do experiments. Yeah. Like you've done chemical measurements almost the entire part of your degree you've had so far. Okay. So this is the overall outline. I'll never point that out again, but here you go. Okay, so like biochemical measurements with a microelectrode and a nanopipette. I don't know if you guys have ever seen these things, but anyways. A microelectrode is going to have a tip that's small enough to implant in a fruit fly's brain. That's less than a millimeter, so pretty small. This is going to be an electrode that's going to measure the neurotransmitter molecules released by a nerve cell in response to a chemical stimulus. So you stimulate the brain, you detect the electroanalytical result, and it actually is a polarimetry result. And so it pulses and then goes down over time. Okay. If you know some biochemistry, you know it's releasing the ions and then reuptaking. Okay. That's what you're seeing here. So it's the response that's released in response to that stimulus. The electrode's active region has dimensions of microns, so it's 10 to the negative 6 meters is the actual active region. So you can actually very precisely target various different regions, though it can be very difficult to do that. Actually doing it can be very difficult. A nanopipette is going to be positioned 10 to 15 microns from the microelectrode. Again, a micron is going to be a micrometer, right? 10 to the negative 6. Okay. I didn't make that decision. That was biology people probably. It's going to deliver nanoliter samples, so 10 to the negative 9th liters of various reagents. These will be used to stimulate the neurotransmitter release. And so you can put a little bit tiny portions of different samples, substrates, and find out which one causes the responses. Okay. The injection of 1 picomole, 10 to the negative 12th mole of acetylcholine, releases 0.4 micromolar, just 10 to the negative 6 molar, of dopamine. This will diffuse to the electrode, generating this electrical current, which is going to be measured in nanoamperes. This is one of the reasons this is used quite a bit, is because electrical currents, can be measured very sensitively. Okay? You can amplify those signals a lot, actually. And so you can make very tiny measurements. This measurement is actually an illustration of the need for units of measure that cover many orders of magnitude, in case you're wondering, i.e. the powers of 10. Look at how much of a pain this would have been to write out. Like, doesn't it look painful? Don't you feel sorry? Yeah. It was unpleasant to read, wasn't it? Yeah. Because 10 to the negative 6, 10 to the negative 9th. You can't compare anything because the prefixes, right? You need prefixes. It makes it much faster. Okay. By the way, this is kind of cool experiments. This is how they determine like the effects of different drugs and stuff on a brain. Typically not a human brain, because that's illegal. There's like human rights now and stuff. Damn ethics. Ooh, no, that's good. Who here's taking ethics? The rest of you will get ethics. Don't let me color your ethics. Okay, so SI units actually stands for the Système International de Units. All of you have probably heard of that before, several times maybe. So the SI units are going to have fundamental units. These are the base units, which all other units are derived. There are actually compound units as well that are going to be combinations of these other units. The examples of your SI unit for specific quantities are these ones right here. Here we have length, which is the meter, mass, which is the kilogram. Mass kilogram is actually kind of unique because it's one of the few ones, actually I believe the only one if I remember correctly, that has a prefix. Every other unit does not have prefixes. Second, which is S, of course, Kelvin, which is the absolute temperature scale. Everybody remembers why degrees Celsius is degrees, right? Degrees Celsius and degree Fahrenheit are relative scales. So they have an arbitrary zero. Kelvin has an absolute zero, which is there is no heat energy. Everything's frozen in place, not randomly vibrating. In case anybody didn't know, temperature and really heat as an extension of that are actually measurements of randomized kinetic energy. Okay. So then we have the amount of a substance. This is going to be the mole or MOL. The electric current, which is the ampere, capital A. These right here are actually derived from those other units. So here we have the Newton, which is measure of force, which is derived from these units up here. Here we have pressure, which is the Pascal, which is again derived from the other units, and energy, joule, which is again derived from the other units. So these right here are some of the different elementary charge. So your SI units are actually based on your physical constants. All SI units have been defined from physical constants of the universe in some way, shape, or form now. Finally. It took a while and a lot of money. Okay? In fact, it cost $20 million of $2010 to finally redefine the kilogram, so it wasn't some random set of weights scattered around the world. Yeah, there's a certain number of silicon nuclei. So very, very difficult to do, but we got it. So this is the elementary charge, which is E, which is actually the charge of an electron. And that's charge of an electron in coulombs. Speed of light in a vacuum, right here. This is also how like the meters are done, in case you're wondering. Planck's constant, right here. Fundamental constant of the universe. Avogadro's constant. These are kind of derived things that you'll notice that their units are kind of weird, right? And that's because we kind of came up with what we wanted for units and what we wanted to measure for units. And then we found these things. And then we had to like work backwards to define them. Yeah. So, yeah, this number is purely because we needed to match AMU numbers to moles. And so this number was come up with. It matches the AMU numbers on the periodic table with grams per mole, right? There you go. Boltzmann constant is right here, denoted with a K, lowercase k, unperturbed ground state, hyperfine transition frequency of 133 cesium. Don't worry too much about that one. You probably won't encounter that much, but it is one of the fundamental constants. Okay. And that's that right there. Luminous efficiency, this is right here. This is like the candela. Luminosity. Yeah. Time, length, and these were how they were actually defined. This is actually why you need this really weird thing here, is because we needed some way of telling time. And because we're within time, and time changes depending on your velocity for the objects within that velocity, we had no standard way of doing it. So we measure it against the cesium atom decaying. Okay. That actually one might be changing soon. There's a proposal to change that. So based on a quantum effect, actually. So we'll see. These right here are your mass, kilograms, and stuff. I'm going to stop going through these, but does anybody have any questions about them? Okay. You've actually heard most of these before. For example, you've probably heard of radian before, back in math. That's the definition right there of a radian. Okay, so these right here are some of the other SI units that have derived from these other units. For example, we have frequency is how many times something happens in 1 second, right? And that's a hertz. Okay. Force, Newton, that's actually its units right there. Okay. You may have noticed that I typically give a periodic table thing that has some of these constants spelled out on it. Okay. Anyways, that's Joule right there. You can actually use these units, by the way, to derive other things from these, like how much energy would come off if you have so many kilograms moving so much speed per second. Those relationships can derive these joules, right? Because that will actually give you eventually the energy, won't it? Okay. And so you can actually rederive all these other ones from each other and those constants I gave you before. Okay. This is electrical resistance. That right there is volts, of course, which is electrical potential. Charge coulomb. All right. So let's talk about prefixes real quick. Everybody remembers prefixes, right? Mega, giga, nano. Okay. So prefixes are actually multipliers, aren't they? They're the same thing as nano 10 to the negative ninth, right? If you were to replace nano with 10 to the negative ninth times within that system, you would have done that, right? Congratulations, same thing as prefix. They allow the expression of large or small quantities relative to your base unit without having to put that entire mathematical explanation. And so you can standardize one unit for the entire thing and then go through and list a bunch of numbers that are comparable without a bunch of zeros everywhere. Much easier to deal with. Now, what you'll typically see is that prefixes are going to be every third power of 10, except for the ones that are very close to the base unit. So the ones that are very close to the base unit, we break it out into every 10th. Okay? As we get further away from that base unit, we just do every 10 to the third. Because you can write hundreds numbers. Nobody really complains about writing numbers in the hundreds, right? So, yeah. So don't forget that 10 to the 0th is 1. So the base unit actually is 10 to the 0, right? That's the base unit. Okay. That's no prefix. All right. Anybody have any issues there? No. Fantastic. This right here is your prefixes. You may not have actually seen some of these before. They're very, very rarely used. But like Yoda is the sort of thing in Zeta that you see in astronomy. Okay? It's like size of the universe sort of stuff. Size of solar system, size of universe. Okay? And that's where you'd see those things most often. They're quite large, 10 to the 24th, 10 to the 21st. Then you go down, you have exa, peta. These are like really, really powerful computers, right? Exabyte, petabyte sort of stuff. You do see them, but again, it's not super common to see them, okay? This is where it starts becoming much more common is tera. You've also heard of terabyte probably. Or terabit. Gigabit. That's your internet connections probably. Half a gigabit. Okay. Megabytes. Like a small movie or something, right? A little video that you download. Also my PowerPoints, because first I'm super inefficient. Kilobytes, my Word documents I make you download. Okay. And that's 10 to the 3rd, 10 to the 6th, 10 to the 9th. Remember, it goes every 10 to the 3rd, right? Okay. This is hecto, by the way. I don't know if you guys have seen this much ever. Anybody ever used hecto before? Yeah. What you'll notice is most of these ones up here, after the 10 to the 3rd one, when you get it bigger, it's a capital. Okay, it's one of the easy ways to remember that. When you're close to it, it's still the lowercase. Okay? And so the kilo, hecto, and deca, not deci, deca, as in decade, right? which is actually the root word for 10 years, decade. Okay. That's 10, of course, DA. And then that's hecto, that's 100. Then this is deci, like decimal. And this one's centi, and I think you all know these pretty well. Pico might be the one that you stop knowing, like picometer. And those are the sort of distances that you would see within like an atom. Okay, picometer distances. Femtosecond is the sort of things where like you see nano transitions, and you'd actually see like electrons zooming around if you go like femtosecond measurements. Okay, that's the sort of thing you need to see an electron actually like pop in and out of existence and move very, very fast. Atto, zepto, and yocto are down here. You'll notice they actually mirror this stuff up here. Okay. Kind of interesting, right? And that's because, again, they're similar root words in Greek. And so they mirror each other because they mirror each other in terms of this positive, this is the negative one, right? Positive, negative. Okay. Kind of if you remember one, you can kind of work out the other if you ever forget, okay? I've had to do that sometimes. I'm just like, what? How often do you think you're going to use these? Almost none at all. I'm going to be honest. If you're in the right field, you might use femto. The rest of the universe almost never uses any of those. Okay. Very, 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 very uncommon. Okay, let's talk about the upper atmospheric ozone. So the upper atmospheric ozone is going to be very important because it's going to absorb ultraviolet radiation from the sun that can cause damage to living organisms and cause skin cancer. It's going to be expressed in relative numbers using prefixes. So, for example, the altitude is typically going to be expressed as kilometers, right? And that's how you'd convert the meters number in scientific notation to the kilometers right there. I'm probably not going to actually work any of these sort of things out unless we get to something a little more difficult, because I kind of have an assumption you've done more unit conversions than you probably ever wanted to. So peak ozone pressure is represented in pascals. But notice that'd be a kind of a pain to write over and over and compare with things. And so what we do is we use a prefix. We're going to use millipascals. So these are whole numbers here. Okay. And so typically you use millipascals when you're representing the peak ozone pressures. And so right here, we actually see that completely. So we see here the altitude in kilometers. And then what we see is the pressure right here in millipascals. This is the ozone partial pressure, which is a direct correlation through the ideal gas law, right, of the amount of ozone you have at that layer. Okay. Because remember, moles is directly related to pressure when you're talking about gases. Okay, and so what you see here is that this is the typical ozone layer. It's not really a layer per se. What it is a larger concentration that tails off into lower concentrations as you get further away. Okay, it doesn't have any really defined spot. It does bob up and down over time. It changes, it warps, etc. Okay. This one right here is actually the normal stratospheric ozone on August 2021. This right here is an ozone hole in October 2021. Okay. So ozone holes actually shrink and expand. It has to do with the polar temperatures and weather. Okay. We can go into it sometime if you want, but not in class because it takes a little while to build up. Okay. And you can see here, this is the ozone hole. The ozone concentration goes way down. What ozone does is it breaks apart whenever it gets hit by high energy light, such as UV radiation. Okay. And this breaking apart consumes that UV radiation. And so it actually consumes the two highest energy bands of UV radiation, one being consumed in the very, very upper atmosphere that is actually causing ozone production. ozone weighs more than the oxygen and most of the other gases around it. It sinks down in the atmosphere and tends to collect about this level right here because that's the density of it. Okay. And then the lower frequency, lower energy UV radiation hits that, breaks it apart into O2 and O, which then reacts with different stuff. Okay. When we put basically anything that devolves into free radical chlorine, a big one being, have you guys ever heard of this before? The ozone layer and ozone holes and okay, okay, kind of. All right, so we used to use, and we still do to some degree as a refrigerant, specific gases that are not reactive basically at all at sea level. Okay, they're only really reactive when they get hit by very high frequency light. And we didn't really realize at the time when we were using them that they would end up going up into the upper atmosphere. Then they'd be exposed by high frequency light, and it causes chlorines to come off as free radicals. And what those do is they actually do a chain reaction. Remember how we had the chlorine reactions in organic chemistry for anybody that's taken it? We'll get to those pretty soon, actually. And what they are reactions that remake that chlorine every time. And so the chlorine actually acts as a catalyst and breaks apart all the ozone. Okay? And that means if you break apart all the ozone, it's going to deplete it. And there's not going to be any that's going to capture that second highest energy UV radiation. Okay? Now, that second highest UV radiation actually would kill you if you're exposed to it long enough. It's the vast majority of skin cancer. Okay? It's also what gives you sunburns. If you're ever out, like you can have the low energy for hours and not have a significant sunburn. The UVB, which is the second highest energy one, that gives you sunburns. Just being 1 to 5% of the light hitting you gives you sunburns pretty quick, actually. Yeah. And if you were to have the full brunt, that not blocked by ozone at all, if we completely destroyed that ozone layer, plants would only last about 15 minutes. It would have wiped out all the life on the surface of the plant in about 15 minutes-ish. Let's give it maybe an hour or two. So that first day, it would have, everything's gone. And then the only stuff live on Earth, caves, and about 10 feet into the ocean. Yeah. Yep. So we almost destroyed all life on the planet. And the only time environmental legislation has been successful in all of the history of humanity is in 1974. And we came up with a treaty to no longer put materials that are going to produce chlorine into the atmosphere, that chlorine gas, Cl free radical, actually, and the Montreal Protocol. And that has actually gotten weakened, partially because the EU paid people to destroy gases like that. And Chinese factories found out it was cheaper just to make the gases and then charge the EU to destroy the gases. And so when the EU stopped doing that, the Chinese threatened to release all the gases and destroy the planet. Yeah. You didn't know that, did you? Then the Chinese government did step in finally. They worked out a deal, though it was a deal, not what the hell were you doing? Anyways, let's talk about some important habits for scientific calculations here. So you write units besides each number in a calculation. You guys have probably gotten this from me before, or at least your general chemistry professor. Write your dang units. Cancel your units. Write your units. Write your units. Hopefully you have a voice in the back of your head that's going to say that. You're going to then cancel identical units in the numerator and denominator because they cancel out. This habit's going to ensure you know the units of your answer. It also flags if you make any mistakes. You'll notice whenever I work things out, I am always going to write all my units first, and I rarely fill in numbers until I need to. Okay? Because I have to erase less stuff if I just work the units out first, right? Like, it's so much easier. If you intend to calculate pressure and your answer comes out with units other than Pascal, which are these right here, or another unit of force area, what do you know? Yeah, that wasn't right, was it? I have to fix something. Okay. Okay. Faulty units can be costly. I don't know if any of you have heard this one before. This is kind of an interesting one. So in 1999, a $125 million Mars Climate Orbiter spacecraft was actually lost by NASA. They messed up. Have you guys heard this one before? Oh, this is a good one. So keep in mind, this is $125 million just for the craft. And NASA is not efficient. So we're probably talking 1999 money of 2 times that. Okay? And that's 1999 money. Now money, you're talking an extra doubling of that or close to, right? So now money would be at least 50% more, maybe doubling, depending on the parts. And so you're talking a huge investment, big project that was really supposed to show how great an understanding of our Mars was supposed to go up so well. The engineers who built the spacecraft calculated thrust in English units of pounds of force. Jet Propulsion Laboratory engineers received the information and thought it was metric unit newtons. So they gave it the wrong unit because nobody wrote the units. Yep. Nobody caught the error until they launched the damn orbiter. And so it was given faulty navigational commands because remember, it's like a 15-minute lag between here and Mars. If you had the perfect signal transmission, it'd still be more like a 15-minute lag. And so instead of going to the Martian atmosphere, it plunged through the Martian atmosphere, started trying to brake when it was 100 kilometers lower than it's supposed to be, which guess what happens when you try to brake way lower in an atmosphere? Wham! Right into the planet. Goodbye. This was like 10 years of development and time of some of the best scientists on the planet and hundreds of millions of dollars. And all because of a stupid mistake that their general chemistry teacher almost certainly told them, write your damn units. And so there's no better demonstration of write your units. Numbers without units don't have meaning, do they? Yeah. And if you see a number without a unit, never, ever guess. Check. Okay. So the SI units, these are going to be intentionally internationally accepted system of measurement in science. Older, more common units are often encountered. You know what the sad part is? It's not even about being old or common. That, yeah, sometimes it's just inertia. Like in the United States, inertia. But you know what? Even in new fields that didn't exist before this, that have no reason to use old units, like environmental sciences, you still catch people going between 10 different units for the amount of CO2 in the atmosphere versus other gas in the atmosphere versus this. And it is sometimes very, very, very intentional. They literally don't want you to be able to go back and look at something else and figure out, oh, this was a meaningless difference. This thing varies within a month 10 times the amount they're measuring here. Okay? This freaking ridiculous difference, it didn't matter. Right? And it's both ways. So be very careful whenever you're looking at something very politically motivated. There's a lot of money on the line. If you start seeing weird units being used that they're not the SI units, really look. Okay? Because they will try to fool you. A lot. People will play games with the math and with the units. Okay? So calories, this is an inertial thing. It was actually the original measurement because it's heating up water, 1 gram of water, 1 degree Celsius. So very oftentimes used. That's joules right here. Everybody knows the calorie. This calorie is different than the calorie in food. Oh, I'm past time, aren't I? Okay. Yeah, please do. Okay. Mile, kilometers, pound, kilograms. There you go. All right. You have a great one. Oh, no. I'm almost exactly on time, right? Woo. We're doing good. We are getting it.
So if you in organic chemistry, you have to talk about expert from the bookstore being weird.
Yes.
And I know what you're